Hi, my name is Tian Long. I'm a PhD candidate in the University of Pennsylvania from Department of Chemical and Biological Engineering. So I'm studying direct self-assembly behavior of soft matter in Professor Chen and Mosuji's group. Specifically, my project is about spatially varying alignment of soft materials using non-uniform magnetic field. So first, I want to introduce a little about what is direct self-assembly and why we are interested. We know self-assembly is some materials can spontaneously form some ordered structure to lower their free energy. And direct self-assembly means we can use some external force to guide the self-assembly process, such as using shear flow, electric field, or magnetic field. Our group has been working on using magnetic field to do the direct self-assembly of block polymers for years. The reason why we use magnetic field is it's contactless, space pervasive, it doesn't have electric breakdown compared to electric field, which makes magnetic field very intriguing from the perspective of scalability, and also it allows us to approach the sample surface in any field direction. But the main problem of using magnetic field is most soft materials doesn't have a high enough magnetic susceptibility and entropy, which means they're not responsive enough to magnetic field. So we choose to use liquid crystalline polymer, which has a much larger susceptibility and entropy than a normal polymer with random coil nature. A lot of work has been done on unidirectional alignment by using uniform magnetic field. And now we want to change from unidirectional alignment to spatially varying alignment by using non-uniform magnetic field. We envision by patterning the magnetic field by arrays of magnetic particles, we can make programmable, spatially varying nanostructures, so we can regulate the wave and matter transport within the materials and maybe provide some complex functionality. We believe this can be useful in soft active materials, in making ion conducting membranes, or doing lithography. So my research focuses on spatially varying alignment of bulk polymers, and we start with a single cobalt block. The block polymer used is PO-PMLC, which is a block polymer with a liquid crystal component side chain. We blended with 6-OZB, which is a commercial liquid crystal, to reduce the critical field, which is needed for alignment, and with a molar ratio R equals to 0.18. By finite element analysis of magnetic field, we can find that when we apply a uniform background field to the cobalt block, the cobalt block will distort the uniform magnetic field by strengthening the field intensity left and right side, but weakening the top and bottom. We also got corresponding experimental results by POM. We can see with the polarizer 45 and 135 degree, the left and right side region becomes brighter, which means the material in these two regions are aligned by the strengthened field, but top and bottom cannot be aligned by the weakened field. We also compare these results with a copper sample. The copper sample doesn't show a brightness change around the copper, which helps us to exclude that this texture change is only induced by surface anchoring of liquid crystal or thickness change of materials. So we can conclude that by using the cobalt block to distort the uniform background field, we can selectively align the block of polymer. We also investigate how the system will respond to varying background magnetic field. We can see as we increase the background magnetic field, the bright region becomes broader and broader, which aligns with our expectation. So we can imagine the alignment is actually the competition between the magnetostatic energy and thermal energy. So the bright region is actually the place where magnetostatic energy is much larger than KT. And as we increase background magnetic field, the bright region will become wider and wider. We'll also try to describe how the light intensity varies with respect to the distance away from cobalt and under a different background field. So our basic idea here is we treat each pixel as an NVT ensemble, so the light intensity should follow, say, Boltzmann distribution, which contains an energy term, and the energy term is a function of magnetic field. And the magnetic field is spatially varying here, so it's a function of distance away from cobalt and a function of background field. So in this way, we can relate the light intensity to the distance away from cobalt and the background field. But this formula needs to be further discussed in detail. If you have some idea, you're welcome to reach out to me. We also show that this approach can be broadly applicable. We tried the block polymer mixed with 6-LCB, mixed with ARM257. We also tried homopolymer. They all work. And we believe as long as you find the proper molar ratio and the proper magnetic field, by blending block polymer or homopolymer with various free messenger, these spatially varying alignment can all be achieved. Our next step is to get direct evidence from AFM. We want to directly see how the nanostructure transition from order to disorder. We also want to make the cobalt block into small pieces and make them into arrays so we can pattern the magnetic field and further pattern the alignment. This work is actually a starting point for a bigger picture, which is spatial programming of soft matter. Our goal is to develop strategies for programming structures of a range of soft material systems, including liquid crystal polymer, which is mentioned here, and the nanocomposites. We want to incorporate the nanoparticles into those liquid crystal polymers and impart different functionality and manipulate their anisotropy. We also want to try some novel materials such as ferroelectric liquid crystal. And the spatial varying methods could be the patterned magnetic field, as mentioned here, and we also want to combine different fields to make novel structures. We also want to utilize the autonomous experiments platform in our lab and do something which can be hard for human to do. Finally, thanks for watching the video, and if you are interested in anything or you want to discuss with me, you're welcome to send me an email.